Hi, I'm Lauren, and today I'm going to present joint work with Anapan Medurata, Tariq Alahi, and Rick Sarkar on privacy-preserving detection of path bias attacks in Tor. Tor is an anonymous communication network, allowing users to access websites or communicate anonymously. It does this by unlinking the client from its destination. In Tor, the route between a client and a destination consists of 3 hops. The route is selected by the client and begins via a randomly selected entry relay named a guard. It then continues to a randomly chosen middle and exit relay before reaching its destination. In this scenario, what is a path bias attack? In green, we see an example circuit formed under normal operation of Tor. Now suppose that an adversary has compromised some guard and exit relays, shown in red. It is bad for the client if their circuit passes through both a compromised guard and a compromised exit relay. During a path bias attack, when a client uses a compromised guard, the adversary identifies if the circuit is not using a compromised exit, for example via traffic fingerprinting, and drops that circuit. This results in a new circuit being built, which may pass through the compromised exit. If not, the process can be repeated. The malicious guard may decide if all, or only a fraction of, the circuits passing through the compromised guard, but not a compromised exit, are rejected in this way. Using this attack, when a client uses a compromised guard, the adversary diverts more circuits through the compromised exit than would occur in the normal operation of Tor, therefore compromising a larger volume of circuits than they would by just passively controlling some guard and exit relays. Our goal in this work is to detect attacks of this form. The adversary's goal is to compromise circuits and to avoid detection. Our approach to detection will be as follows. We will count the frequency of occurrence for each guard-exit pair in the observed circuits. On the x-axis here, we see examples of guard and exit relay pairs. On the y-axis, we see the number of times each of these pairs was used in a circuit, their frequency. We will compare the expected frequency on the left to the observed frequency on the right. In this way, we can identify pairs where the observed frequency is unexpectedly high. An expected frequency distribution can be obtained using a Tor consensus document. As I will cover again later, we find that using the expected distribution obtained via the consensus document was a reasonable choice for this comparison. Given the path bias attack detection problem and the general detection approach described, in the remainder of this presentation, I will first discuss our basic algorithm and provide a result demonstrating that a small data size suffices for detection. I will then discuss how to perform this detection in a privacy-preserving manner and outline how a binning mechanism can be used to provide reliable detection, even with relatively small data volumes. I will then describe an extension of this algorithm which increases resilience to adversarial reporting via voting. Finally, I will discuss practical aspects of our algorithm, including the computational and communication overhead, and experimental results demonstrating its performance. In our algorithm, what do we mean by an unexpectedly high observed frequency, and what is our detection criteria for an attack? Here, on the x-axis, we have the frequency of occurrence increasing from left to right. Suppose for a specific guard-exit pair, if there is no attack, the observed frequency will be centered around the expected frequency f, as shown in grey. However, suppose that if there is an attack, the observed frequency will instead be centered around a different, higher value. This new value is given by a multiplicative increase to 1 plus phi times the original expected frequency f plus an additive increase of lambda. The attack size is then described by the parameters phi and lambda. Our detection criteria will be that we will say there is no attack if an observed frequency falls below the halfway point between the expected frequencies with and without an attack. Otherwise, we will say that there is an attack. Obtaining more data will narrow the distributions, therefore reducing the overlap and making detection more reliable. In order to detect an attack with confidence level 1 minus beta, for a guard exit pair who have a probability p of being selected for a circuit, then the required data size is given by 12 ln of 1 over beta times 1 over p times 1 over phi plus lambda over f squared. In order to preserve user privacy, we will obtain the observed frequencies while satisfying differential privacy. Given the frequency distribution we saw previously, differential privacy ensures that the presence or absence of any one circuit that occurred is obscured in the aggregate result. This is achieved by adding random noise to the observed frequencies. Then, a third party, or the aggregator, who view the aggregate frequencies cannot infer the presence or absence of any specific circuit. The level of privacy provided is defined by a parameter epsilon. Roughly, differential privacy ensures that the probability of obtaining the reported frequency f, given that a circuit I was not included in the database, is within a multiplicative factor of e to the epsilon of the probability of obtaining that same frequency if circuit I was included. A smaller value of epsilon makes the multiplicative constant smaller, and so provides a stronger privacy guarantee. Within our algorithm, we add another layer of privacy via additive secret sharing. Additive secret sharing is a method to compute the sum of some values without revealing those individual values. It divides a piece of information into n shares, and that information can only be reconstructed by combining all n shares. Now that we have covered the basic problem, our general detection approach, and have briefly overviewed the privacy methods used, we will discuss how the algorithm itself operates. The middle relays will be our data collectors. They first initialize the database of guard exit pairs and their corresponding frequencies, and the noise and secret shares required for differential privacy and additive secret sharing, and send the secret shares to some share keepers. After these initialization steps, during the data collection phase, when the middle relays see a circuit from a guard to a particular exit, they increment the appropriate frequency counter. At the end of an epoch, the middle relays and share keepers send their values to the aggregator. The aggregator then combines them to obtain the frequencies previously discussed and performs the statistical test to detect pairs with unusually high observed frequencies. The operator of the algorithm can then decide how to proceed given these test results. We have now covered the basic algorithm and will move on to discussing two challenges for this detection approach. Firstly, in practice, there are many pairs with very low expected frequencies. The frequency distribution looks more like the following, with some high expected frequencies, but also a tail of low expected frequencies. The noise due to differential privacy disproportionately skews the very low observed frequencies. As a solution, we place relays with similar probabilities, based on their bandwidths, into bins. In this case, low-frequency relays will be included in a larger bin, up to a specified maximum bin size. So, how does this help? As an example, if we consider the guard 1 exit bin 4 pair here, the frequencies are combined, and the relative effect of the random noise is less severe. Now, instead of obtaining frequencies for guard exit pairs, we obtain frequencies for guard exit bin pairs. Note that in situations where data from all middle relays is not available, a subset or random sample of these middle relays can be used. In this case, if the reporting relays represent a proportion P of the overall middle relay bandwidth, then the required data size must be scaled up accordingly. We now come to a second challenge for our algorithm, which is the possibility of misreporting middle relays. For example, if the adversary also compromises Q of the M available middle relays, then at reporting time, they can send some very large or very small frequency values for various counters in order to skew the final aggregate frequencies in an attempt to hide their attack. While sampling somewhat reduces the effect of compromised middle relays misreporting, a more effective method is to have each middle relay send a binary vote for each pair, indicating if their observations mark that pair as part of an attack or not. Where the middle relays originally sent their observed frequencies to the aggregator, who performed the test, the middle relays now perform the test themselves and send a binary vote to the aggregator for each pair. This approach means that each middle relay contributes only a 1 or 0 to the count, instead of contributing a potentially unbounded frequency for each reported frequency. The advantage of this approach is that there is now a high probability of correct detection, despite the compromised middle relays. The data size here is determined by the required accuracy of each individual middle relay's test. The operator of the algorithm can decide on the best trade-off between accuracy and data size for their use case. We have now covered the basic algorithm and two extensions addressing challenges for the algorithm. We will now discuss the practical use, beginning with its computational and communication overhead. Firstly, an example of the overhead costs given a setup with 3,000 guard relays, 3,000 middle relays, and 100 exit relay bins. In this scenario, the database of frequencies for the pairs will be 2.4 megabytes in size. For the middle relays, there are computation and communication costs. The communication costs are up to 2.4 megabytes, as the information about the frequencies or secret shares is sent to the aggregator or share keepers. In terms of computational cost, obtaining the bin takes on average 13 milliseconds. The initialization steps take on average 536 milliseconds. Both of these occur once per epoch. In an epoch where 1 million circuits were observed by a middle, incrementing the counts takes 450 milliseconds on average. For the network itself, the communication costs corresponding to each middle relay communicating their database is up to 7.2 gigabytes in an epoch. If there is an epoch every hour, then this would represent approximately a 0.0003 proportion of the daily traffic on the Tor network, given that Tor sees around 517 terabytes of traffic per day. In order to empirically evaluate the effectiveness of this technique, two datasets were collected. Firstly, real-world Tor was collected to compare circuits built by Tor clients to the expected distribution given by a consensus document. Around 353,000 circuits were generated using Tor clients from the Central, Europe, US West, and Asia regions. The datasets from different regions were combined, since that is what middle relays would see in real life. The second dataset contained 1 billion synthetically generated circuits. Note that there is approximately 1.2 billion circuits observed in Tor per day. This larger synthetic dataset was generated in order to allow experiments on larger dataset sizes, which were beyond the real-world Tor setup due to the expense and time costs. The expected probability distribution these synthetic circuits followed came from a Tor consensus document. We also varied the attack parameters and adversary resources. From real-world Tor, we found that examining the top 10 guard-exit pairs, they occurred around 1.96 times more frequently than expected. There are two ways to incorporate this into our algorithm. Either we can accommodate this by appropriately setting phi and lambda in order to detect attacks larger than this effect, or the expected distribution, which was originally set using only the consensus document, can be updated accordingly. An advantage of our scheme is that over time, it can be used to discover the appropriate updates to the expected distribution, and the longer it runs, the better these updates could become. From the synthetically generated dataset, we find that the detection algorithm performs well even for strong privacy guarantees, with the degradation in accuracy caused by strong privacy parameters mitigated using more data and by appropriately setting the additive constant from the detection criteria lambda. In this figure, the x-axis represents the privacy parameter epsilon, and the y-axis shows the algorithm performance in terms of the F1 score. In the left-hand plot, as we move from right to left, we see that the F1 score is decreasing as the privacy parameter becomes smaller. However, on the right-hand side plot, we have adjusted lambda in order to take into account the expected amount of noise being added in each case. In this scenario, any degradation in performance due to a stronger privacy guarantee is less severe. We also saw that attacks spread over many smaller relays are harder to detect. Here, the red and blue lines demonstrate that a powerful adversary using large or medium-sized relays can be easily caught using a small amount of data. However, the green line shows that an attack spread over many smaller relays requires more data to achieve similar performance. The red line in this plot shows a particularly difficult scenario using very small relays. As we can see, increasing the data size and appropriately calibrating the binning parameters improves performance. To conclude, in this work, we have considered path bias attacks in Tor. We provided a data-efficient detection algorithm with provable privacy and utility guarantees, which is robust to adversary misreporting. We saw that accuracy improves rapidly with the available data size and the size of the attack. Finally, our scheme could also be used to detect other types of deviations within the Tor network and is not limited to detecting path bias attacks alone. Thank you for listening.